Welcome to this NPTEL lecture on techniques and principles of modern radar systems. Now, we were discussing detection, realistic detection thing. There we have seen the probability of false alarm and probability of detection based SNR calculation from Albert-Sim's equation. Now, today we will see the target fluctuation, and as I said at the end of the previous class that Peter Swayam has developed models for tackling those fluctuation thing. So, I can say that the target cross section RCS is fluctuating, number one. So, also the radar is scanning. So, its antenna beam is moving, whether mechanical or electronic steering, but the beam is moving. So, aspect of illumination that is changing. So, that means the beam position is also changing. So, that will also add to the fluctuation, etc. And so, that in the path, propagation path, if suppose with this change of beam aspect, there may be a new path where a new scatterer may be present. So, that will change the return. So, that means this is a propagation effect. Also, there may be some fading in one of those aspects. So, that time the fading will change the received echo signal, etc. So, that is why Peter Swayam considered all these, and he described 4 models, 4 such basic cases, 4 models. As a name I should write, because these models are now very standard, and Peter Swayam, he actually modeled it. And for each model, he described, the model is described by a particular scenario, and so 4 models, I should say that described by a particular target as well as propagation condition. So, a target is having 2 different condition, propagation condition also is having 2 different conditions. So, with permutation you can with combination you can say there are 4 models will come. Actually, he had 4 such models. And finally, what is the outcome of the model? He calculated these models with the help of the model. He calculated SNR required as a function of PD, PFA and N. N is the number of integrated pulse, because that N is now crucial, because how many N's you are doing, that will affect the whole scenario, that whether the scenario is stationary or not. So, let us start with the 4 models one by one. Case 1 or Swayam model 1. Here he says that first let us, for the, I will underline these 2 terms, target and another is propagation condition. So, what he did, or I will, before describing the model, let me see the target RCS fluctuation. He actually calculated and gave two types of target, two types of target RCS fluctuation. So, actually here there is a difficulty that RCS is, the symbol of RCS is sigma, and in probability distribution sigma is the standard deviation. So, these two may get confused, try to understand clearly. So, basically we are finding the probability distribution of target RCS sigma. So, for that the statistical parameter, the standard deviation we will write as sigma average. So, he wrote that some type of two types of target RCS fluctuation. One is this type, P sigma is equal to sigma average e to the power minus sigma by sigma average, sigma greater than equal to 0. So, sigma is the RCS, sigma average is the statistical parameter. So, and what is sigma average? Let me define it. It is average over all values of target RCS. The moment I am calling average, it is a statistical parameter. Okay. Now, actually this type of fluctuation, he Peter Swelling analyzed targets and he showed that those target which have many scattering centers, many independent scattering centers, but no dominating scatterer. So, each one is independent and they affect. So, if there are many such, in practice actually if there are 4 5 such independent scatterers, then this the target RCS fluctuation is in this shape. This is called Rayleigh scatterer. So, this one what I said, that is for Rayleigh type of scatterer, Rayleigh scatterer. He named it under the famous scientist Rayleigh. Actually, you can see that this is something, the counterpart in noise is the Gaussian distribution, that if there are large number of independent scatterers, but no dominating scatterers, then by central limit theorem we say that the individual distributions may be anything, but with large number they becomes Gaussian. This is similar to that. In case of RCS, if there are no dominant scatterer, but there are many independent scatterers. In practice, if there are 4 5 independent scatterers without any dominating one, then the target RCS fluctuation distribution is given by this. Actually, you can see that this is not a Rayleigh PDF, scatterer is Rayleigh, Rayleigh scatterer. Actually, this is an exponential distribution. Actually, exponential distribution is the squared voltage distribution of Rayleigh. So, this thing, but Peter Swilling named it after Rayleigh scatterers. So, we will say that for Rayleigh scatterers this is the thing, and another thing I will say number 2, that if there are, so here I can say no dominating scatterer and many independent scatterer. That makes a Rayleigh scatterer. Whereas the another type of targets are that one dominating scatterer and there may be many small scatterers, but one is clearly dominating. So, that time this fluctuation, the distribution for that will be given by so, he said that the targets, radar targets, they will fall into one of these categories, number 1. Also, the propagation condition, that can be 2 types. One is the echo pulses received from a target on any one scan are of constant amplitude throughout the scan. That means this is a stationary scenario. Basically, as I am scanning, the propagation condition is not changing, so I am getting the same amplitude. Obviously, I cannot get the same amplitude because it is going and the thing is coming differently, but what the meaning is, it is a stationary propagation condition. Stationary propagation condition. Whereas the second one is that each so actually the name of this thing is that this is called slow fluctuation case, slow fluctuation, and each pulse, each echo pulse is uncorrelated from the next echo pulse even during a scan. That means the propagation condition is very fast changing. So, one pulse I have sent, then again I am sending a pulse, the echo I am receiving, these two are totally uncorrelated. So, this is a fast fluctuation, fast fluctuation. So, based on these, what Peter Swelling said, you see that target RCS fluctuation, that is 2 distribution, propagation condition 2, he clubbed one set from there, one from here, and by that he made the model. So, that model we will now discuss. Case 1 or swelling model 1, that it says that the target RCS fluctuation is of Rayleigh scatterer type and propagation condition is slow fluctuation. Case 2. The second type, he didn't give the name, or dominating type, that one, and propagation condition is fast fluctuation. Case 3. Target RCS fluctuation I made a mistake. This is corrected. This is first type. Rayleigh type. Target RCS fluctuation, here I will say second type, and propagation condition case 3. So, slow fluctuation, or sometimes it is also called scan to scan. That means, in a scan throughout there are no fluctuation, in the next scan there is fluctuation, slow fluctuation. And case 4, case 4 is obviously the target RCS of second type, target RCS fluctuation, and propagation condition is fast fluctuation. So, swelling model 1, swelling model 2, swelling model 3, swelling model 4, and the no target fluctuation and no propagation condition stationary. So, that is called sometimes case 0, sometimes also called case 5. So, that says non-fluctuating. So, actually case 5 is nothing but our original radar range equation model, non-fluctuating target RCS, non-fluctuating propagation condition. So, what he did, Swayam made that he gave some graphs. So, PD versus SNR per pulse in dB, and so and PD he gave from 0.1 to 0.99, and he so this is the 0 model, then this is 2, this is 4, this is 3, and this is 1. So, he said that his models will be like this, and he said that for a given PD you can find SNR from these graphs, that what is the SNR required, and also in all 4 cases the sigma average is to be substituted in radar range equation instead of sigma. In our original radar range equation we said only sigma, now it should be sigma average with the proper from the distribution you will have to find what is sigma average, that you will have to put, and for SNR you will get this. So, you see that from this we can say that for a given PD, for a given PD, maximum SNR is demanded by the curve 1. So, case 1 puts more demand. Here you can see, here also you can see that case 1 always is the most demanding. So, if we do our calculation based on swelling case 1, then we know that we are having the most conservative estimate, but sometimes that is an overkill. So, that is why people then go in the depth of what is the actual model of the target as well as the propagation condition. And fluctuating, this shows that fluctuating targets will require more SNR than the non-fluctuating case, that you can see from the 0 model. So, always it is for any given PD you see always some extra SNR is required, like here you see for this PD this is the extra for model 2, this is the extra for model 4, then this is the extra for model 3, and this is the extra for model. So, now that is why people also do one more thing, that that they call the fluctuating loss. Because of the target fluctuation and propagation condition fluctuation, that loss is coming. So, I can put that as a loss. This is called fluctuating loss, in dB. So, what does it mean? The extra SNR required per pulse due to fluctuation. So, that people have plotted LF versus PD. So, here you can see that you can have -5, 0, 20 like that, and here actually above 0.5 only these are valid. So, people have shown now the plots are something like this. So, we will see that 1 and 2 they are both of the Rayleigh scatterer type, and 3 and 4 both are of the second type. So, their LF is similar, and people have from these fluctuating loss they have made an empirical formula that this is valid above PD is equal to 0.5. So, what they have done, okay. So, the modified radar range equation is like this: PT G A sigma, this n is the number of integration, then 4 pi square k Boltzmann constant, T naught b the noise figure, then S by n for a single pulse, and then LF whole to the power 1 by NE. Now, this NE is 1 for case 1 and case 3 is equal to N for case 2 and 4, and LF is equal to 1 if you have case 0, which boils down to the original equation. So, this is the modified radar range equation after all our thing. So, you have a extra fluctuating loss and this SNR calculation per pulse. So, this one you can calculate from Albert-Symons equation. So, that means you know now that what is the PFA for a given PFA, given PD you are calculating this, then depending on the scenario you are modifying this. So, that completes, this is the final thing, that modified radar range equation. So, this is the final outcome of your study. Now, we can find out the range of the radar. Now, sometimes clutter or nowadays with warfare etc., a deliberate jammer, they may be many times more than the receiver noise. So, that jammer power etc., and then if the noise becomes very high, noise or jamming thing, then your VT will be crossed many times. So, you will get lot of false alarm, and that time the probability of detection will fall much below 0.5, and so detection is meaningless there. Now, in automatic radar thing, then there is a need to overcome that, because if it is seen that a lot of false alarm is coming, that means definitely the noise condition has changed. So, that noise condition can be sensed. Actually, the so that means the clatter or jammer, that power that is sensed automatically. So, what they do? They now take the echoes and find their correlations, and from that they can actually they can put 2 tap delay lines in both sides of a particular echo, and they are compared with real target's video signal, and accordingly an estimate of the noise sigma estimate is formed, and accordingly the VT is adjusted. So, the receiver which does that is called CFR. That is an advanced topic, just I am telling that it is constant false alarm rate receiver, CFR. So, how to make it automatically without any operator? That is a very good work of radar study. So, basically the basic idea is same, that if you want to maintain constant false alarm rate, then you will have to always have an estimation, dynamic estimation of the environment. That is done by estimating the what is the power of the noise. So, that gives you an estimate of the sigma of the whole scenario. This sigma is the standard deviation, that means statistical parameter of the noise or jamming or clatter thing. So, based on that, again from that basic equation you can calculate, to maintain constant false alarm rate, what should be my VT. It is an exponential variation. So, you can have that thing, and then you put that VT, you will see that automatically the false alarm rate will come down and it will be maintained that thing. So, with that I conclude this detection thing, this statistical detection. Now, you know that okay, if I am making any measurement, when we have a probability of our success, that is in this case probability of detection, and with a given probability of false alarm, that means with a given noise statistics, we can always say that this will be the radar range. So, with all these things, that model is the modified radar range model. We have described that. With that, you can analyze almost all the cases that you will encounter in your professional life. Thank you.